We present Chorus, Learning Canonicalized 3D Human-Object Spatial Relations from Unbounded Synthesized Images. The goal of Chorus is to enable 3D human-object interaction reasoning, in a self-supervised way. Given a category keyword of an object as input, Chorus aims to reason about the 3D HOI, represented as probabilistic occupancy distribution. Chorus learns the occupancy distribution in the canonicalized space, which can be used to infer object distribution for humans in any pose. Chorus can also infer possible distributions for various semantic types of HOI, where semantics can be given as natural language description, or optionally can be further specified with body parts. Humans interact with objects in specific ways. For example, we wear hats on our heads, ride a bike holding handles and stepping on the pedals. While this is known to us, it becomes challenging when teaching to machines, as providing supervision with 3D HOI annotation can be hard to scale, due to numerous variations. An alternative approach can be leveraging 2D images from internet, as they are scalable and easy to get. However, the method becomes ambiguous when learning 3D, as they do not contain explicit 3D annotations. Also, anonymously collecting 2D images can return the images without HOI, which will hinder the quality of results. Our intuition is that we can mitigate this problem by synthesizing 2D images of HOI, and use humans as cues for conveying 3D spatial relationships, from 2D knowledge. The key challenge then is, how to synthesize 2D data regarding the semantics of HOI, and how to unify 2D spatial knowledge, into 3D space of any posed human. Chorus tackles each challenge in two phases. The first phase, the dataset generation phase, starts by generating prompts that describe the semantics of the HOI, and creating a database of multi-viewpoint images faithful to the HOI prompt, using diffusion models. The second phase is the aggregation phase, where we extract 2D cues from the images and aggregate them to 3D canonical space. By cleverly selecting the images to aggregate, we can infer distribution per semantic type of HOI. Let's dive into details. Given category keyword, we use large language models to generate prompts that describe plausible HOI, which allows us to represent much more diverse and open set of interactions than representations used in prior works, such as action categories. Using a set of generated prompts, Chorus leverages text conditional diffusion model to create an image database. We then apply keypoint-based filtering to remove images that contain unsuitable images for HOI learning, such as images with erroneous humans. Consequently, we predict 3D humans from the images. Using the 3D humans, we calibrate the camera for the generated image, by using humans as anchor. Chorus utilizes object segmentation as 2D spatial cues, which are aggregated to human-centric 3D space using disambiguated cameras. However, naive aggregation of 2D cues will lead to disperse accumulation, and cause high variance, due to remaining pose diversity. Thus, Chorus chooses to aggregate 2D cues in pose canonicalized space, to assure coherency between rays. By canonicalization, we can also learn human pose conditional object distribution. By cleverly selecting the images to aggregate, we can infer the distribution per semantics of HOI type. Aggregating all images from all prompts, return marginalized distribution, for the most probable interaction type. Selecting the images only generated from specified prompt and aggregating them, gives us a distribution specific to that described prompt. Here are a few example results of Chorus, applied for various categories. To note again, the high values denote the high probability of object occupancy. Here are the results for semantic clustering. See this surfboard example. While the object distribution for a person balances on a surfboard shows the mode below the feet, the object distribution for a person carries a surfboard exhibit the mode around torso and arms, which is the part used for carrying surfboard. An interesting example is also shown for the category bicycle. For the prompt, the commuter standing next to bicycle, we can see a donut-shaped distribution. Thinking that a person can head any direction while standing next to a bicycle, we can expect a rotationally invariant distribution, a donut shape. Chorus is novel, thus provides opportunity for myriads of applications. Here is an example application, single image HOI reconstruction. Given an image, we apply instance segmentation to find the main object category, where we consequently apply Chorus as prior, to infer the object distribution. We then apply threshold and run marching cubes, to get the object mesh. Our method does not require any template mesh. Thank you for listening.